Hello everyone, my name is Ryan. I work here at the Tomas Rivera Center, and today we're going to be covering a General Chemistry 2 problem. It's topic 14.5, and it's going to be calculating the pH of a weak acid solution. Okay, so first we need to start by Ka of both HCN and the Ka of HNO2. You notice that the Ka of HNO2 is bigger. So if you remember your rules, the bigger the Ka, the more acidic something is. Or you can also say it in terms of pK, so the smaller the pK, the more acidic it is. So this is a very important concept for you to remember. So for instance, we can say that because the K value of hydrochloric acid is 1.3 times 10 to the 6th power. So here you can tell that hydrochloric acid is very acidic, and you know this because it's a strong acid. Okay, so the first thing we're going to do here, so now that we said that HNO2 is a stronger acid than HCN by looking at their K values, now we want to calculate the pH of the solution, and we're going to do so by looking at HNO2. In this case, we have so let's first draw out the equilibrium of HNO2. So you have HNO2 in an aqueous solution. Okay, so here it tells you that it's a source of a proton, and since HNO2 is the strong acid here, we could calculate the pH based off of this. The reason being is because since HCN is the K value is so small that we could essentially ignore it and just focus on the stronger acid, in this case being HNO2. So when we perform an ice table on this compound, you know that initially you have, according to the problem, you have 5 molar of HNO2, and we're going to have 0 of this H plus and NO2, and again, since this is a weak acid, you know that it's not going to undergo 100% dissociation. So we're just going to say minus X because we know that some of this is going to dissociate, but remember, not all, because it's not a strong acid. And we'll just say plus X plus X. So at equilibrium, this would be 5 minus X, and this would be X and X. So then now we can use the Ka equation, which is, we know that it's H plus and NO2 minus over your weak acid, and then in this case it would be HNO2. So the problem gave us Ka, so the Ka being 4.0 times 10 to the negative 4 equals, and the H plus here, we said that it was X, so we can just plug in X for it, and NO2 minus, we said it was X as well, and HCNO2, it's going to be 5 minus X. Okay, so let's just rewrite this, and on top would be X squared. And if you remember, you're able to essentially say that X equals 0 because since a small amount of X or a small amount of acid dissociated, since it's so small, essentially we can just say it's 0. So in this case we'll just say X squared over 5 and just ignore the X. and we can verify this. So let's just verify that it's within a 5% range, because if it's over 5% range, then x will be significant. So we can do so by using this equation. It's going to be x over the concentration of your acid that you were given, and then times 100, which equals. So before we do this, let's first solve for x, and up here by just doing algebra, by multiplying on both sides by 5 and square rooting, you would get x equal to 4.5 times 10 to the negative 2. Okay, and then now we can verify this to make sure it's within the 5% range. So we're going to plug in this x in here, and that should give us 0.9%. So this is definitely within the 5% range. Again, remember, if it was over 5%, then we would have to actually count x as significant and leave it in the equation. But since it's 0.9%, we can just ignore x and just say x equals 0. Okay, so then now that our x is 4.5 times 10 to the negative 2 power, we can just basically plug this into our pH equation. You know that pH equals negative log of your H plus ion right here. So pH, H plus was our x, because if you remember, this was our x and it was for our H plus. So just plug it into equation. So then this pH should be 1.35. Okay, so then when you go back up to problem statement, we calculate the pH right here, and again we didn't use the other acid because since the acid had such a small K value, we could basically ignore it in a way and just use our stronger acid to calculate the pH of the solution. So then this would be the pH of the solution. Now the second part to this problem, it wants us to calculate the chloride ion at equilibrium. So by doing that, let's get the K value of your HCN that was given to us in the problem statement. It's 6.2 times 10 to the negative 10. So 6.2 times 10 to the negative 10. And we know that Ka again equals your H plus, and in this case it's going to be Cn minus your cyanide over the concentration of HCN. Okay, and from the step that we did before this, we solved for H plus, so we have that. And we also have the concentration of HCN. Again, the concentration of HCN was given to us in a problem statement, which is 1 molar. And we can say that this would be the concentration of HCN at equilibrium, because since it's again a very weak acid, only a very, very small amount of it's going to dissociate. Essentially, it will be equal to, or it will be close to 1. So we can just say at equilibrium it will be 1 molar. And so we're going to be solving for your cyanide ion. So 6.2 times 10 to the negative 10, and then your H plus was 4.5 times 10 to the negative 2. Let's call your cyanide ion X, and then this will be 1. So then X will just equal to 1.4 times 10 to the negative 5th molar. Again, this is just your concentration of your cyanide ion at equilibrium. So then recapping this, again, in the beginning we only used the HCNO2 as our acid in order to solve for the pH of the solution, because this one was a stronger acid when comparing HCnO2 and HCN. That's directly looking at their Ka values. And an important concept to know is that the bigger the Ka, the stronger the acid, and then the smaller the Ka, the weaker the acid. And then for pK, it's the smaller the pKa value, the stronger the acid, and then vice versa. And we use an ice table in order to solve for our X, and then X would be the concentration of our H plus ion, and from that we just plugged it into the equation to the equation for pH, which is just negative log of your H plus ion, and we solve for the pH. For the second problem, we use a K value of your hydrogen cyanide in order to solve for the Cn ion at equilibrium. And again, the concentration of cyanide of hydrogen cyanide at equilibrium is just 1 molar, because since it's a weak acid, only a small of it will dissociate. Essentially, we can just say that the same molar of it will be present at equilibrium. In this case, it will be 1 molar. And solving for it just gave us 1.4 times 10 to the negative 5th molar. And if you have any further questions, you can come visit us here at the QLab. Again, we're located on the 2nd floor of JPL. Thank you everybody for watching, and please subscribe to our channel and like us on Facebook. Thank you, and have a great day.